Hello everyone, I am Nikhil Tiwari. So this is Me206 S2 course project. The topic is plane strain forging using ANSYS. It is done by team 20. So the problem description is as follows. We have to perform 2D strain analysis of a squeeze forging of annealed copper rectangular block. The block is placed between two steel dies and a pressure load is applied on the upper die to compress the copper block. The problem statement is we have to determine the forging pressure required to reduce the height of bar by 25%. The block has a square cross section with height and width of zero point 0.1 meter. So let's try to understand some concepts. So forging is a manufacturing process that involves shaping of metals using localized compressive forces. The blows are delivered with a hammer, often a power hammer, or mostly dies are used and the work is compressed between them. So the ANSYS uses finite element analysis that is based on finite element method. In this, a substance is divided into several elements which are analyzed separately. For each element in the mesh, we specify U that contains all the displacements including the rotation and has a size equal to the DOF of the system. And for each element, the equation F is equal to Ku, where F is the matrix of normal forces and components, and K is the stiffness matrix. So K is actually a square matrix, and F and U are column matrices. So this gives us the distribution of force in the element, and using appropriate boundary conditions at each element, we can club the solutions of the elements and get the solution for the entire body. So what is meshing? So actually, to solve a problem, we divide the body into several small elements by a process known as meshing. In our case, we use 2D 8-node quadratic plane strain elements with quadratic meshing to model the copper block. So actually, we are using plane strain conditions for the forging. Therefore, there are 4 nodes, and at every node there are 2 degrees of freedom. So that is translation in x direction or y direction. There is no rotation. So it is 8-node quadratic plane strain element. The material properties that are used. So the source for all this information is Practical Stress Analysis by Finite Elements book by Dr. Brain J. McDonald. So for annealed copper, the Young's modulus is 110 GPa, Poisson's ratio is 0.34, yield stress is 33 megapascal, failure strain is 0.16, and for the die steel that we are using, that is actually tool steel, Young's modulus is 210 GPa, Poisson's ratio is 0.27, and we assume that dies are made up of steel and do not deform during forging. So this is our assumption. So let us try to understand tangent modulus. So tangent modulus is defined as slope of a line tangent to the stress strain curve at a point of interest. The tangent modulus is mostly used to describe the stiffness of a material in plastic range, and it is denoted by ET. So as you can see here, after elastic region, the curve no longer has a constant slope. So we can just approximate the slope using tangent modulus. So some formulas are given here. The resultant yield stress due to deformation is given by sigma y plus tangent modulus into strain. The strain is ln of h0 upon h1, where h0 is the initial height and h1 is the final height after deformation. Tangent modulus is given by ultimate tensile strength minus yield stress divided by failure strain minus proof strain, where proof strain is 0.002. Coefficient of friction in our problem is assumed to be 0.05. So the average pressure required to reduce the height of block of width b from h0 to h1 is given by p is equal to y1 e raised to power mu b upon h1, where mu is the coefficient of friction and h1 is the final height, b is the width. So implementation on ANSYS. So our first step is to choose a static structural analysis system because we assume that there are no vibration effects on application of loads, and we add materials that are required. In the second step, we make the geometry width 0.05 meter and height 0.1 meter. We take vertically symmetric cross section because the same thing happens on both sides of the symmetry line. So to reduce the computation and time required for the computation in ANSYS, we draw a symmetry line and take one of the symmetric section. In third step, we model the system, provide surface and mesh to the substance. Then we set the boundary conditions for the experiment. Then we solve for stress, strain, von Mises stress, and strain and reaction forces for the solution. So finite element modeling. So we do a 2D plane strain model of half cross section through forging problem need to be developed. So 2D 8-node quadratic plane strain elements are used since there is a barreling effect. So during forging, the friction forces at the die work interface oppose the spreading of material near the surface, while the material in the center can expand more easily. So the result is to create a barrel shape at the butt. So therefore, we cannot approximate it using linear plane strain elements. So we use quadratic plane strain elements. Then material models. So linear isotropic model for tool steel is used. So E is 210 GPa, Poisson's ratio is 0.27, and bilinear isotropic elastoplastic model for copper for the bar. So E is 110 GPa, Poisson's ratio is 0.34. Yield stress is 33 megapascal, tangent modulus is 167 megapascal. So in bilinear isotropic hardening process, both stress and strain change even after reaching maximum plastic deformation. But the change in shape cannot be observed clearly in the bilinear hardening process. So we will look at it in more detail when we do the project. So the geometry that we use is height of block is zero point 0.1 meter, width of block is 0.05 meter, width of die is zero point 0.1 meter, and an area defining one half of the cross section through the bar or die assembly was generated, and it has been shown here. So due to fact that bar would be deforming significantly during FE simulation, a very fine mesh is used for rectangle representing the bar. The dies are not assumed to deform in forging, they just transfer load, so a coarse mesh was used. So this is the mesh that is used. This is a quadratic mesh, the element type is quadratic, and the element size is 0.0025 meter. So the boundary conditions are that the dies are treated as a rigid body as they are assumed not to deform, and we are not interested with what is happening in the die as well. The area defining the upper die was constrained in moving in the horizontal direction while it was allowed to move in the vertical direction. The lower die was constrained in all the directions. So if we now look at the results of the simulation, so the directional deformation comes out to be like this. Clearly the maximum compressive deformation occurs just below the upper die, and it is 25% of the original height. Then normal elastic strain, its variation in the body comes out to be like this. The normal stress is varying like this in the body, and as we can see, the normal stress is symmetric about the symmetry line. If we take the horizontal symmetric, the x-axis, if we take x-axis as a symmetry line, then normal stress is symmetric about that. Then this is von Mises stress distribution in the body, and this is equivalent elastic strain or von Mises strain distribution in the body. So we get a characteristic shape for forging. So that has to be there, and we got that. Then the results are, so on applying a pressure of 86.62 megapascal on the upper die, the maximum deformation comes out to be 0.029 meter. So actual deformation required is 0.025 meter. So thus the theoretical and experimental values are close to each other, and it verifies the theory. We will show it in the project. So thank you. That's it. So